Imagine your immune system, designed to protect you, suddenly turning against your own body. This is the reality for millions living with lupus, a chronic autoimmune disease. Instead of attacking only germs, the immune system mistakenly targets healthy tissues and organs, causing widespread inflammation. Lupus can affect joints, skin, kidneys, blood cells, brain, heart, and lungs. Symptoms vary widely. Some experience mild issues, others face severe complications. Common signs include a butterfly-shaped rash, extreme fatigue, joint pain, and sensitivity to sunlight. Because these symptoms mimic other illnesses, lupus is often called the great imitator, making diagnosis challenging. People with lupus experience unpredictable flares, periods when symptoms worsen, triggered by stress, infections, or sunlight. Remission periods, when symptoms subside, can follow, making daily life unpredictable. The disease impacts not just the body, but also emotional well-being, often leading to anxiety and isolation. Visible symptoms like rashes or hair loss can affect self-esteem. Support from loved ones and medical professionals is crucial. Understanding lupus is the first step toward better treatments and hope. Now, let's talk about a virus most of us carry, Epstein-Barr virus, or EBV. EBV is one of the world's most common viruses. About 95% of adults have been infected. Most people catch it in childhood, often without symptoms. Sometimes, especially in teens and young adults, it causes mononucleosis, extreme fatigue, sore throat, fever, and swollen lymph nodes. After recovery, EBV doesn't leave. It hides in your body for life. The virus takes up residence in B cells, a type of white blood cell, and can remain dormant for decades. For most, this lifelong infection is harmless. The immune system keeps it in check. But in a small number of people, something goes wrong. Scientists have long suspected EBV might trigger certain diseases later in life. Clues have linked EBV to autoimmune diseases and some cancers, but the exact connection was elusive. Understanding how EBV operates is key to solving this medical mystery. Let's see how this virus spreads and persists. EBV spreads easily, mainly through saliva, hence the nickname kissing disease. Sharing drinks, utensils, or even being near someone who coughs or sneezes can transmit the virus. Most people are exposed in childhood, often without symptoms. Early infection is usually mild, but catching EBV as a teen or adult can cause mononucleosis. The symptoms, fatigue, fever, sore throat, are actually your immune system's response. After the initial infection, EBV retreats into a dormant state inside B cells. Once infected, you carry EBV for life. The immune system controls the virus, but can't eliminate it completely. EBV has evolved to hide from immune surveillance. Occasionally, the virus reactivates, especially if the immune system is weakened. During reactivation, EBV can be shed in saliva, making you contagious even if you feel fine. This cycle of dormancy and reactivation is why EBV is so successful. Its persistence is central to its role in disease. EBV's survival strategy is to hide inside B cells, the very cells meant to defend us. B cells produce antibodies to fight infections, but EBV hijacks them, inserting its genetic material and keeping the cell alive longer than normal. This creates a stable reservoir of infected cells. By hiding in B cells, EBV evades detection by other immune cells. The virus produces proteins that prevent the infected B cell from self-destructing. This manipulation can disrupt normal immune function. Most of the time, the immune system keeps EBV in check, but it can't eliminate the hidden virus. If this balance is disturbed, problems arise. EBV's proteins can interfere with B cell behavior, sometimes causing the immune system to make mistakes. Researchers believe this long-term manipulation may trigger autoimmune diseases like lupus in some people. Could EBV's presence in B cells be the missing link? For years, the link between EBV and lupus was just a suspicion. Nearly all lupus patients have been infected with EBV, but correlation isn't causation. The big question, how could this common virus trigger lupus? In 2022, Stanford researchers provided a breakthrough. They studied the antibodies lupus patients produce, autoantibodies that attack the body's own proteins. They focused on a viral protein called EBNA2 and a human protein called Rho. Astonishingly, they found a lupus autoantibody that binds both to the human Rho protein and to EBNA2. The viral and human proteins share a strikingly similar structure, a phenomenon called molecular mimicry. The immune system, trying to fight EBV, creates antibodies that also attack the body's own cells. This was the smoking gun scientists had searched for. EBV's disguise tricks the immune system into launching an autoimmune attack. This discovery provides a direct molecular link between EBV and lupus. It's a game changer for understanding the disease. Let's break down this case of mistaken identity. The immune system is like a security force, trained to spot invaders by their unique markers. EBV's EBNA2 protein closely resembles a segment of a human protein. The immune system creates antibodies to fight EBV, but these antibodies can't distinguish between the virus and the body's own cells. It's like mistaking an innocent twin for a criminal. These confused antibodies attack both EBV and healthy tissue, a classic autoimmune response. The initial attack can expose more self-proteins, leading to even more autoantibodies. This snowball effect explains how a simple viral infection can trigger a chronic disease like lupus. The virus isn't trying to cause lupus, it's just using mimicry as a survival strategy. But in genetically susceptible people, this resemblance sets off a devastating chain reaction. The immune system, tricked by EBV, becomes its own worst enemy. This is how a common virus can spark a lifelong illness. One of lupus's biggest mysteries is why it affects women far more than men. About 90% of lupus patients are female. Hormones, genetics, and immune differences all play a role. Estrogen boosts immune activity, making women's immune systems more aggressive. This can be helpful, but also increases the risk of autoimmune mistakes. Lupus often flares during hormonal changes, like menstruation or pregnancy. Genetics matter too. Many lupus-linked genes are on the X chromosome, and women have two. A faulty gene on one X can be more active in women. The EBV discovery adds another layer. The viral protein interacts with human factors that are more active in women. In women, the combination of hormones, genetics, and EBV creates a perfect storm for autoimmunity. The virus provides the spark. The female immune system fuels the fire. This helps explain lupus's gender gap. Connecting EBV to lupus opens new doors for treatment and prevention. Until now, lupus treatments have focused on suppressing the whole immune system, often with harsh side effects. With a specific trigger identified, researchers can target EBV directly. One promising idea: develop a vaccine against EBV to prevent infection and potentially lupus. Advances in vaccine technology make this a realistic goal. For those already living with lupus, new therapies could block the interaction between EBV proteins and human cells, or target only infected B cells. This would spare the rest of the immune system, reducing side effects. Of course, developing new treatments takes time and rigorous testing. But this breakthrough gives scientists a clear target. For millions with lupus, it's a shift from just managing symptoms to aiming for prevention or even a cure. The future looks brighter than ever. The EBV lupus link is more than a scientific milestone. It's a beacon of hope. For years, lupus's cause was a mystery, making the disease feel random and isolating. Now, knowing EBV is a key trigger changes everything. It shifts the fight from an unknown enemy to a known one. This knowledge empowers patients, reducing stigma and self-blame. It could also lead to earlier diagnosis, screening for specific autoantibodies before major symptoms appear. Early intervention could prevent irreversible damage. The discovery energizes researchers to pursue new strategies. One day, we may prevent lupus with a vaccine, or treat it with targeted therapies. For those affected by lupus, this breakthrough is a promise of a better future. The great imitator may finally be unmasked and defeated.